Hi, Michael Wolf, PGI Compiler Engineer. Today we're going to be talking about pinned memory, what it is, and why you might want to use it when programming with OpenACC on a GPU. What is pinned memory? Pinned memory is a block of contiguous memory in the system memory that can be used for efficient data transfers to the GPU. Let's take a look at how these systems are put together. So here I have a multi-core CPU, and I'm going to attach it to a highly parallel GPU. Today, the connection between the two is a PCI Express bus, which is a really great I/O bus, not such a great memory bus. The CPU has a very large system memory, many gigabytes. The GPU is attached to a smaller but higher bandwidth device memory. When I have data in the system memory, a big array here, and I want to copy that data to the device or bring the data back, but let's look at one direction first. Copy the data to the device memory. I'm going to allocate some space in device memory, and now I want to do the copy of the data over there. The actual data transfer is done by a little engine in the GPU called the DMA engine. It's for direct memory access. And the CPU will program the DMA engine saying, here's the start address, here's the end address. Start address here, number of bytes to move. The start address, well, the DMA doesn't know about virtual memory or page translation. It can't take a page fault. So it needs a physical address and needs the bytes to be contiguous in physical memory. So it's going to start transferring data from the system memory over to the device memory, but it can't do this from the user space, the virtual user space. Because this is one big array that's contiguous in virtual space, but in physical memory it's paged. And some of the pages may not be contiguous. Some of the pages may have been paged out to disk. The DMA engine can't handle that. So what happens is either the NVIDIA CUDA device driver or the OpenACC runtime has to allocate a pinned buffer in system memory. Pinned buffer would be a block of contiguous memory that cannot be paged out. That's the pinned part. And then copy the data from the user space and page everything into the pinned buffer, and then tell the DMA transfer engine to move the data across to the device memory. So this data copy is extra overhead that you need to do to get data from one device to the other, from one side to the other, and bringing it back is the same in reverse. What we're going to be looking at is how to allocate the user data in pinned memory directly to avoid this extra data copy. Today we'll be doing our experiments on two identical machines. Each of them is a dual socket Haswell, 16 cores in each socket, 32 cores total, 64 threads available for execution. And each is connected to 2 Pascal GPUs. In our experiments we'll just be using the first one. To clarify, the pinned option only affects allocatable data, dynamically allocatable data. It does not affect static or global or stack data, function local data. Variables in the stack or global data will be transferred using the normal transfers, meaning with the extra copies to the pinned buffer. If you're a CUDA Fortran programmer, there's a pinned attribute for allocatable arrays, which gives you the same advantage as the pinned option for OpenACC. In fact, if you use CUDA Fortran data with OpenACC kernels, arrays with the pinned attribute will give you the same advantage. Data transfers will happen directly into or out of the user data. So here we're going to be looking at the SpecExcel OpenACC swim benchmark. The swim benchmark has an outer timing loop that runs for many iterations, and each iteration of that loop, it does a data transfer from the device to the host to do a check to see whether it's converged. The pinned option will improve the computation speed by improving the speed of that data transfer, of the data update, because you'll be doing direct transfers into user space. So I've got my two machines. They're in the right directory. We're going to build the SpecExcel swim benchmark. In the first case, we're going to build with the normal option, t equals Tesla. And because I'm running on a Pascal, I'm going to specify the compute capability. And while that's building on the other machine, I'm in a different directory, and I'm going to build the second machine with Tesla pinned. I'm going to run the ref dataset in each case. In the upper window, it's the normal build. In the bottom window, it's the pinned build. What we're going to see is, if there's any justice in the world, the upper window will take about 10 or 15 seconds longer than the lower window does. So the two cases where you might want to be using pinned memory is if you're doing a lot of data updates or data transfers between the host and device, pinned memory transfers will be significantly faster. And if you're doing a lot of asynchronous operations and asynchronous data transfers, the data transfers for asynchronous operations will not only be faster, but will impact your execution less because the transfers will be truly asynchronous from the user space. So here we can see the lower window has already finished. It took 33 seconds elapsed time. The upper window still took a little bit, it just finished, took 15 seconds longer, 48 seconds. That's a summary of how to use pinned memory with the PGI compilers and how to improve the execution of your program if it's being dominated by data transfers between the host and device. I hope you enjoyed this video. Come back for another video with tips and tricks on how to use PGI compilers.